Okay, hello everybody. So my name is Anastasia Koivikko and I work in Bio-Inspired Materials and Robotics Group at the Tampere University of Technology, as said. And today I will tell you about our screen-printed curvature sensors which we fabricated for the soft robots. So at first, what are soft robots? They can be defined as robots which consist of very compliant materials, and these kind of materials can be found in nature and especially in living organisms. And here you can see one great example of this kind of animal, octopus. Its whole body is very soft, but it can still move really fast in the water and quite fast actually on the ground too. And it can handle very delicate objects with its tentacles. And here is one robot which was inspired by octopus. So to make these soft robots, we need soft actuators, and these kind of actuators there are already quite many these kind of actuators. Here you can see one. It's called Pneunet, and the design is from Soft Robotics Toolkit website. And in this work, we used this design. And these kind of actuators are usually quite passive, and the real challenge is how to make them smart, because the sensors have to be stretchable and flexible too. So different kinds of ways have proposed capacitive and resistive and optical sensors. And here's one liquid metal-based sensor. But the challenge with this sensor is that the material is quite hard to handle. And in this work, I present our solution to use screen-printed sensors. Okay, so first, is how these smart and soft actuators were made. First step is to make the sensors. So the conductive ink was added on the screen lying on the elastomer sheet. And the ink was transferred through the substrate through the mesh. And the next part was to integrate these sensors to our pneumatic actuator. As you can see, the actuator consists of two different parts. So the upper part includes the expanding pneumatic chambers, and the lower part includes the strain limiting layer. So when the actuator is pressurized, the chambers are expanding and the actuator is bending. And our sensor was placed on the strain limiting layer. And all parts were bonded with silicone adhesive. Here you can see our smart pneumatic actuator. And to calibrate our actuator, we can measure different kinds of things. We can measure the resistance of our sensor and the pressure in the chambers, and we can estimate the bending using video and machine vision. Bending kappa. And here is the image of our smart actuator. Here's the sensor. And here you can see the sensor design. The ink which was used was a silver flake-based conductive ink, and here's the image of that. So now we have our actuators, and then we have to characterize them. So we did 30 slow cycles, and the cycles were slow to avoid the dynamic effects of viscoelasticity. And here's the results of our characterization. Here's the resistance of the sensor, and here's the pressure in the chambers and the curvature which was estimated using the machine vision. As you can see, there's quite big hysteresis, but it's consistent to previously reported hysteretic behavior of conductive inks. But in the end, as you can see, the behavior is quite linear. And here's the start state and here's the end state. So we had that hysteresis in our measurement, so we wanted to know if it's caused by the temperature fluctuations during the cycles. So that's why we measured the resistance of the sensor while we heated it on the hot plate. And we also measured the temperature during the cycles inside the actuator. And here you can see that it was only 0.3 Celsius, and this caused 0.4% change in the resistance. So the hysteresis was not caused by the temperature fluctuations. So our sensor was straining, and the strain was estimated using two different ways. And the first way was to use this ideal bending relationship. And here's the d is the distance from the neutral plane, and kappa is our curvature. And we got that it's straining 1%. And the other way was use this previously reported gauge factor and the change in resistance. And this equation gave us 2% strain. So they are quite close each other, but this other one is easier to measure, so we concluded that it's more trustworthy and we use that one. Okay, so now we have that actuator which is measuring the curvature. So we wanted to make sure that the resistance is really giving us the curvature values, not the pressure values. So to measure that, we measured the resistance and pressure in 4 different stages. At stage 1, the actuator is in neutral state, and the second stage is driven when it's pressurized and it's bending. The third stage is blocked when the actuator is pressurized, but it's blocked to bend by using hand. And in 4th stage, it's not pressurized, but it's bending, and the bending is done by hand. And these measurements told us that the resistance is more close to curvature than the pressure, but there is still some response to pressure too. And by using simple linear decoupling, we got that 70% of the sensor signal comes from the curvature. And for more detailed measurements and details, please check our paper. So now we had that soft smart actuator, so we wanted to make one application. So we used one common base, and we included 3 actuators of it. So each finger is independent and can be measured and actuated independently. And the scale bar here is 3 centimeters. And here you can see how the actuator is picking an apple. So here's the video of our gripper measurements. Each finger was actuated independently, and the pressure and the resistance were measured. As you can see, they are quite independent, but you can still see some response in the other fingers when one finger is actuated. So as a conclusion, screen printing is a very promising way to integrate these sensors into soft robots because they are very fast to manufacture, and the design of the sensor can be changed very easily. And they are quite cheap, so they scale well to mass manufacturing. Of course, there is some limitations like the hysteresis, but it can be compensated with Braysac type hysteresis models. Or in the end, usually we need only relative change information of the robots because they are moving, so these can be used very well. In the end, I would like to thank you, my group, especially my supervisor Veikko Sariola and Mahmoud Mosallaei and Matti Mäntysalo for the electronics group in the same university. And here's the contact information. Thank you.